This video is prepared based on official accident reports and witness testimonies. November 4, 2010. The world's largest passenger aircraft, a Qantas Airbus A380, departs Singapore's Changi Airport, bound for Sydney on what should be a routine flight. Just 4 minutes into the journey, at 7,000 feet above Indonesia's Batam Island, disaster strikes. Captain Richard de Crespigny commands VHOQA Nancy Bird Walton with 440 passengers and 29 crew members aboard. Two loud bangs shatter the morning calm as the No. 2 Rolls-Royce Trent 900 engine suffers an uncontained failure. Turbine disc fragments hurtle through the left wing, severing fuel lines, hydraulic systems, and flight controls. What follows becomes one of aviation's greatest displays of crew resource management under impossible circumstances. With multiple system failures cascading through the A380's complex networks, 5 pilots worked together to save 469 lives aboard the world's most sophisticated airliner. This is the story of how millimeters of metal thickness in a manufacturing defect nearly caused catastrophe, and how exceptional airmanship, teamwork, and aircraft design redundancy combined to prevent what could have been aviation's deadliest disaster. Against overwhelming odds, skill triumphed over mechanical failure above the South China Sea. Airbus A380 represents the pinnacle of aviation technology. Delivered to Qantas in September 2008 as their first super jumbo. This aircraft spans 73 meters with double-deck passenger configuration, seating up to 525 people. Named after Australian aviation pioneer Nancy Bird Walton, it embodies cutting-edge engineering with fly-by-wire controls and unprecedented system redundancy. 4 Rolls-Royce Trent 900 engines power this 560-ton marvel, each generating 70,000 pounds of thrust. The A380's complex systems include triple redundant hydraulics, sophisticated flight management computers, and backup systems designed to handle multiple failures simultaneously. Captain Richard de Crespigny commands this flight with exceptional credentials, 35 years flying experience spanning military and commercial aviation. His background includes fighter jets, test pilot training, and extensive A380 certification. Today's crew includes First Officer Matt Hicks, Second Officer Mark Johnson, plus 2 check captains conducting training evaluations. This 5-pilot configuration proves providential, far exceeding normal 2-pilot operations. Check Captain David Evans brings decades of experience, while Check Captain Harry Wubbin adds additional expertise. Each pilot contributes specialized knowledge essential for managing the unprecedented emergency ahead. The flight crew's diverse experience, combined with A380's advanced systems and multiple redundancies, creates the perfect foundation for handling aviation's most complex emergency scenario. Today, experience meets technology in an ultimate test of human factors and aircraft design philosophy. November 4, 2010 begins routinely at Singapore's Changi Airport. Flight QF32 represents the final leg of Qantas's prestigious London-Sydney service, connecting 2 hemispheres across 15 time zones. Singapore serves as the crucial refueling and crew change stopover for this ultra-long-range operation. The A380 boards 440 passengers from diverse backgrounds, Australian business travelers returning home, British tourists beginning Pacific adventures, families reuniting across continents. Singapore's efficient terminal operations handle the massive passenger flow with characteristic precision. Pre-flight preparations proceed normally as ground crews service the world's largest passenger aircraft. Fuel loading reaches 320,000 pounds for the 8-hour journey to Sydney. Cargo compartments fill with international freight and passenger baggage weighing additional tons. Captain de Crespigny conducts standard pre-flight briefings with his expanded crew. Weather reports show excellent conditions throughout the route. All 4 Trent 900 engines complete ground tests successfully, showing normal parameters across all systems. At 10:01 a.m. local time, the massive A380 begins taxi operations toward runway 20C. Air traffic control clears QF32 for takeoff into Singapore's humid morning air. The Super Jumbo accelerates smoothly, lifting off at 180 knots with 469 souls aboard. Initial climb proceeds normally through Singapore's controlled airspace. Everything appears routine as the flight heads southeast toward Australia, with no indication of the mechanical time bomb ticking within engine number 2. 4 minutes after takeoff, climbing through 7,000 feet over Indonesia's Batam Island, tranquility explodes into chaos. 2 sharp bangs echo through the A380 as engine number 2 suffers catastrophic uncontained failure. The Rolls-Royce Trent 900's intermediate pressure turbine disc disintegrates, hurling metal fragments at supersonic speeds. The explosion sends turbine pieces slicing through the left wing like shrapnel. Fuel lines sever, hydraulic pipes rupture, electrical cables cut, and flight control linkage is damaged. A brief flash fire ignites in the wing fuel tank before self-extinguishing, narrowly avoiding catastrophic explosion. Captain de Crespigny feels the aircraft shudder violently as debris penetrates multiple systems. "That doesn't feel good," he calmly announces, demonstrating remarkable composure as warning lights cascade across instrument panels. The electronic centralized aircraft monitor displays over 50 failure messages simultaneously. Engine number 2 continues windmilling with massive internal damage, its titanium fan blades twisted beyond recognition. Fuel streams from severed wing tanks while hydraulic fluid spills from damaged lines. The world's most advanced airliner suddenly becomes a flying emergency with compromised systems throughout. Ground witnesses on Batam Island report seeing bright flashes and falling debris. Several large metal fragments crash into residential areas, causing minor injuries but miraculously avoiding fatalities. The engine failure releases enough energy to power a small city, yet the A380 structure holds together. Initial crew assessment reveals the magnitude of damage exceeds anything in training scenarios or aircraft certification testing. Before continuing this investigation, please subscribe to Through the Pilot's Eyes for detailed aviation analysis. Your support helps us research these critical safety lessons. Now back to QF-32's unprecedented emergency. The engine explosion triggers cascading system failures throughout the A380's complex networks. Engine number 1 suffers damage from flying debris, reducing its power output significantly. Engine number 4 also experiences problems, limiting thrust available for recovery. Fuel system damage proves extensive. Thousands of pounds leak from severed lines in the left wing. Fuel transfer systems fail, preventing fuel movement between tanks. The crew faces potential fuel starvation despite carrying adequate reserves for Sydney. Flight control systems suffer severe degradation as hydraulic lines rupture. Spoilers lock in various positions, affecting wing aerodynamics. Slats refuse extension, limiting landing configuration options. The massive aircraft becomes increasingly difficult to control as backup systems strain under unprecedented demands. Electrical failures compound the emergency as power buses trip offline. Landing gear systems malfunction, preventing normal extension procedures. Anti-skid braking systems fail completely, leaving only manual brake control for the 560-ton aircraft's eventual landing. Captain de Crespigny coordinates his expanded crew through systematic troubleshooting. 5 experienced pilots work together, dividing responsibilities across engine management, flight controls, fuel systems, and emergency checklists. Their collaboration demonstrates textbook crew resource management under extreme stress. The A380's triple redundancy prevents immediate catastrophe, but multiple system degradation creates scenarios beyond certification requirements. Today's crew faces challenges no simulator could replicate. With systems failing across multiple networks, Captain de Crespigny orchestrates his 5-pilot team through aviation's most complex emergency. Each crew member assumes specific responsibilities, maximizing their combined experience and knowledge. First Officer Hicks maintains aircraft control while monitoring primary flight instruments. His steady hands keep the damaged A380 stable despite asymmetric thrust and degraded flight controls. Years of training enable smooth coordination with the captain's commands. Second Officer Johnson manages fuel systems and engine parameters, calculating remaining reserves against multiple leaks and transfer failures. Check Captain Evans handles radio communications with Singapore ATC while monitoring backup systems. Check Captain Woobin coordinates emergency checklists and system isolation procedures. The crew's systematic approach prevents panic despite overwhelming failure warnings. Captain de Crespigny's calm leadership style establishes clear priorities, maintain aircraft control, assess damage, and plan safe return to Singapore. His fighter pilot background provides valuable experience managing catastrophic failures. Working through complex emergency procedures, the team isolates failed systems to prevent further damage. They shut down the severely damaged number 2 engine while carefully monitoring the compromised number 1 and number 4 engines. Fuel management becomes critical as leaks continue draining precious reserves. Air traffic control clears QF-32 into holding patterns east of Singapore while the crew assesses their situation. The damaged A380 circles slowly, burning fuel and time while pilots work through unprecedented challenges. Every decision carries life or death consequences for 469 people aboard. Circling in holding patterns, the crew conducts systematic damage assessment while fighting multiple system failures. Engine number 2 remains severely damaged with visible fire and smoke, requiring immediate shutdown. However, engine shutdown procedures fail due to severed control lines. Fuel leak calculations reveal alarming consumption rates from wing damage. thousands of pounds drain away each minute, reducing options for extended troubleshooting. The crew faces critical time pressure as Singapore approaches maximum fuel reserves for safe landing approach. Landing gear systems show extensive damage, preventing normal extension procedures. Manual backup systems require complex procedures while managing other emergencies simultaneously. The massive A380's weight demands precise approach speeds with compromised aerodynamics from wing damage. Spoiler systems malfunction in various positions, affecting lift distribution across the wing. Slats remain retracted despite crew attempts at extension, forcing non-standard landing configuration. Flight control computers struggle to maintain stability with degraded input signals. Brake systems failures prove particularly concerning for the 560-ton aircraft. Anti-skid protection disappears completely while brake temperatures rise from system damage. Manual braking provides only limited stopping power for an aircraft requiring maximum performance. Captain de Crespigny calculates approach parameters with degraded systems while coordinating crew actions. Every system affects others in the A380's integrated design. The crew methodically works through interconnected failures, prioritizing critical systems for safe landing approach. Time becomes the enemy as fuel burns away and system damage potentially worsens during extended flight operations. After nearly 2 hours of troubleshooting and fuel dumping, QF-32 begins final approach to Singapore's runway 20C. The damaged A380 configures for landing with compromised systems throughout, testing both crew skill and aircraft design limits. Captain de Crespigny flies a carefully calculated approach with asymmetric thrust from 3 partially functional engines. Engine number 2 remains shut down but refuses complete isolation due to severed control lines. Fuel continues streaming from wing damage as the massive aircraft descends. Landing gear extends through manual backup procedures after normal systems fail completely. The main gear deploys successfully, but nose gear shows potential problems. Brake system failures eliminate anti-skid protection, leaving only basic manual braking for the 560-ton Super Jumbo. Approach speed increases due to slat retraction and spoiler malfunctions affecting wing aerodynamics. The crew maintains precise control despite degraded flight characteristics, demonstrating exceptional airmanship under impossible conditions. Singapore's long runway provides adequate distance for the challenging landing. Touchdown occurs smoothly despite multiple system failures throughout the aircraft. Captain de Crespigny applies manual brakes carefully while managing asymmetric thrust from operating engines. The A380 rolls down Changi's runway as emergency vehicles race alongside, monitoring for fire or further complications. Ground stop occurs safely with all 469 people aboard surviving the unprecedented emergency. However, the crisis continues as engine number 1 refuses shutdown commands, creating ongoing fire risks with damaged fuel lines nearby. After successful landing, QSOF-32's emergency continues for hours as engine number 1 refuses shutdown due to damaged control systems. Fuel leaks and hot engines create serious fire risks, preventing immediate passenger evacuation through normal procedures. Captain de Crespigny makes the difficult decision to delay evacuation until air stairs arrive at the right side door, away from the running engine and fuel leaks. Emergency responders surround the aircraft while passengers remain aboard for nearly 1 hour until safe evacuation procedures are established. Engine number 1 finally shuts down after 3 hours when firefighters pump foam directly into the intake, stopping the turbine rotation. The massive A380 sits damaged but intact, testament to both aircraft design and crew performance under extreme circumstances. ATSB investigation reveals the root cause as a manufacturing defect in oil feed stub pipes within the Trent 900 engine. Thin-walled pipes, improperly manufactured with walls below design specifications, led to fatigue cracking and oil leakage. Internal oil fire caused turbine disc failure and catastrophic engine destruction. The investigation spans years, involving Australian, Singaporean, British, and Indonesian authorities. Rolls-Royce faces scrutiny over quality control procedures that allowed defective components into service. Manufacturing processes undergo complete revision to prevent similar failures. Qantas temporarily grounds its A380 fleet while Singapore Airlines and Lufthansa inspect their Trent 900 powered aircraft. Multiple engines require replacement after discovering similar manufacturing defects. The incident exposes systemic quality issues requiring industry-wide attention and regulatory response. Thank you for following this remarkable aviation investigation with Through the Pilot's Eyes. Please subscribe for comprehensive analysis of aviation's greatest challenges and triumphs. Qantas Flight 32 becomes a landmark case study in crew resource management and aircraft system design. Captain de Crespigny and his team demonstrate exceptional airmanship, managing the most complex emergency in A380 history through systematic teamwork and calm decision-making under extreme pressure. The A380's sophisticated design philosophy proves its worth despite unprecedented damage. Triple redundant systems provide sufficient backup capability to handle multiple failures simultaneously. Advanced fly-by-wire computers maintain control despite severe structural and system damage throughout the aircraft. Manufacturing quality improvements emerge industry-wide following detailed investigation findings. Rolls-Royce revises production procedures, implements enhanced quality controls, and develops improved turbine overspeed protection systems. The entire oil feed stub pipe production run is scrapped and replaced. Regulatory authorities strengthen certification requirements for uncontained engine failure scenarios. New advisory materials guide manufacturers in designing systems capable of withstanding extreme damage from turbine disc failures. Industry-wide inspections prevent similar defects from reaching operational aircraft. The accident transforms crew training programs globally, emphasizing multi-pilot coordination during cascading emergency scenarios. Captain de Crespigny's leadership style becomes a model for managing complex technical failures through systematic problem-solving and clear communication. All 469 people survived aviation's most complex emergency through the combination of engineering excellence, manufacturing accountability, and exceptional human performance. Their safe return proves that preparation, teamwork, and technology can triumph over mechanical catastrophe,